All right, so this is for the last chapter that we got to get through. This deals with worksheet 14.1. And basically, this is just kind of get wrap your head around a few things here. So one, there are two sets of notes. There's notes 1 and note 2, notes I should say. So I'm going over the note 1, but I'm going to be referring to like examples, like this right, first one here, like example number 2. So you have to look here in terms of the graph. So basically, I'm trying to get your head wrapped around looking at things three-dimensionally. That's pretty much all this is. So don't panic if you say, do I have to remember this average rate that I'm going over? No, this is just kind of seeing to realize that when we are doing derivatives three-dimensional, so you can see a rate of change, what that is in 3D space. Okay. So anyway, so like I said, we're going to start with example 2. So you'll have to look on the second set of notes on the graph and look at that. And for the most part, it's, this is just looking at topology, you're graphing. If you ever gone hiking or anything like that, you've seen these maps before. So we're just going to look at graphing them. So what we have here is now written like f of x comma y, which is referred to as your z equals. So if I look at again like example 2, if I ask you to find an average rate of change if you're climbing, let's say, Saddle Rock. So if you look at that on a map, you basically look at the change of your altitude divided by your change of your horizontal distance. And that's where if you see, look at your lines here, like this, that when these lines are getting closer together here, that means you're going up really steep. When you have lines that are apart, therefore the rate of change is going to be a lot less, which is basically that rate of change. So when we're doing derivatives in terms of the steepest rate of change, obviously from this map here, it would be, let me find some here, it'd be in this area here would be my rate of change, because those lines, I kind of erased it there, those lines are real close to each other. And let's just throw another one in there, and like so on. All right, so that would be your steepest ascent given a function like this when you do the derivatives. Okay, we're just going to look at wrap your head around it and seeing how to do it just mathematically. So if you look on example 2, if you look from, let's say, P to Q, you would see the lines, and you have 3 lines, a distance of 0.8, which would give you 2.4. So that average rate of change would be 2.4 over 2, therefore you have 1.2. So what does that mean? It says your altitude gains 1.2 times the horizontal distance. Okay. So if we go to again example 2, but let's look at figure 2. So if you go from A to B, that average rate would be 50 over times 2 over 200, which would be 0.5. If you look from A to C, that average rate would be 50 times 2 over 400, therefore 0.25. If you look at A to D, okay, that average rate would be 50 times 0 over, it doesn't matter what number. So basically what you're doing is you're just staying level on the contour of your hillside, which is 0. So what is the steepest ascent? Would be here, A to B. So that would be the steepest here, this would be less, and here you're just going along the hillside, you're not going up or down, you're staying level to it. So like I said, when we're doing the derivatives, obviously, you know, when you do derivative, you get 0 here. That means you're going here. And then compare your slopes and all that. Okay, again, we're just getting wrap your head around doing the derivatives of these functions here. Okay. If you go to, let's go to figure 16. Okay, just a little bit more looking at this. So looking at the average rate on this one. Okay, the altitude here would be 0.8, and I said times 3. And your horizontal distance, again, is 2 kilometers. And therefore you have that 1.2 average rate of change. Okay. All right. So anyway, so if you look at, you got your notes, take a look at my notes, look at figure 17, same thing. My answers there. For the most part, just wrapping your head around this topology. Try to do the best on the assignment. I'm not going to ask questions on average rate on the final, so you don't have to worry about doing that. But just kind of seeing if I was doing derivatives of this function, what would you get? Okay, and hopefully you kind of wrap your head around your steepest ascent, the least amount of descent, going up, going down. When would I be on the top of a hillside, on the bottom? Where would be that saddle point? Those kinds of things is what you kind of have to kind of understand what we're doing here. Just thinking that three-dimensional space. So real simple assignment, and I'm going to combine this with 14.2 since this is just a quick, easy thing using your calculator. I am going to put another video together here in a second talking about how to use the technology to graph this stuff out. But right now, this is just going to kind of help you to